Okay, on today's lecture, we will see the most important example of a point process, and this is a Poisson process. I believe maybe most of you are familiar with Poisson process on the line when you consider the sequence of independent events and that occurs in time, like you have the following picture. When you count the number of events that occurs in time, like here, you just draw 0, then on the height 1, you draw the second stage, and so on. So this is the historically the first point process that arises in some applications. But today we will consider it as we will consider the generalization of such an object. So we will consider the Poisson process in general space. So we will see how we can define it. So let us give the definition. So, but before this, we should understand some properties of the measures that we will work today. So, since we will have a deal with usual algebraic operation, like summation, and you know that in probability theory you often consider the sum. You consider the sum of random variables, for example, xi, 1 to infinity, and we will consider summation of Poisson process and so on. So we should understand the background of this procedure. So we will consider in arbitrary space, in space, okay, just X with fixed sigma field X. So as example, you can consider RD with a Borel sigma field on RD, but this construction you can apply for general space. And on this general space, we will consider measure lambda, but not the general, but such that it can be presented as the sum of finite measures. So such that there exists a sequence of measures lambda I, which are finite measures. Lambda are finite measures, and this measure lambda can be represented as sum of finite measures. So this is just for a useful notation. We will call this measures lambda is called as finite measures. So we can see that a measure that we will work with is not finite in a general sense, but we can consider a sum of the a countable summation of finite measures. So why do we need this? This is just because I want later consider the infinite summation of measures. So I just want to specify the class of measures that we will use in our lecture today. So this is S finite measure. And in order to define a Poisson process, we should fix some S finite measure on our space. So let us give the definition of the main object of today's lecture. So let lambda be S finite measure on measurable space X. So I fix measurable space X, but if it's difficult for you, just imagine RD. And a Poisson process, we will omit sometimes point process, Poisson point process with intensity measure lambda is a point process, let us denote by eta, with the following properties. So let me write. So this point process on the space X with the following properties. So at first, we will assume that for each space, each subset from sigma algebra, the random variable eta of b, so this is the number of points at this subset, has the distribution of a Poisson distribution, so this is notation, with parameter lambda of b. Let me recall that that this just means that the probability that eta on b is equal to k is equal to what? So if this is a parameter of the distribution, we know that here we write this parameter, and then lambda of b at power k over k factorial. So we know how the number of particles distributed in a fixed subset. So if you know some subset b, so the number of particles distributed by this law, so and it depends on the initial measure lambda that we fixed. So lambda is non-random, just S finite measure. And here, let me do some remarks before we go forward. Because we should understand what happened when, for example, lambda of b is equal to 0. So when this parameter, when we have the set of 0 measure. So here we can just understand that probability to have 0 points is equal to 1. So here we just use notation that 0 in power 0 is equal to 1. That's it. So you can substitute it here. And if lambda of b is equal to infinity, so we just actually this expression does not fully defined, so we just by assumption we get that the probability that we have infinitely many points is equal to 1. Okay, so this will be our assumptions when we have a set of measure 0 and set of measure infinity, so it can happen. Okay, and I continue the definition. The second assumption for a Poisson process that if I fix any number of disjoint subsets, B1 and so on, Bm, they are disjoint, Pj is equal to empty. Then random variables eta of B1 and so on, eta of Bm are independent. So here important that we should consider the distribution of all number of subsets, that they are mutually independent, because it is not enough just to assume that we have a pairwise independency. So this is important. Okay, so this is the definition of a Poisson process. And let us recall that we gave the definition in the lecture 2 of the intensity measure. And here I told that a Poisson process with intensity measure lambda. So let us understand that that lambda is indeed the intensity measure. And why is it so? Because we know that for random variable which have a Poisson distribution with parameter lambda of b, we know that the expectation of it is equal just to this parameter. So we discuss it on the first lecture when we consider the properties of Poisson distribution. So indeed, lambda is the intensity measure of. Now, the main question when you see some definition is to understand if such object exists or not. Okay, we want to have such an object with some distribution and with the property that number of particles does not depend in non-intersecting subsets. So if I have different subsets B1, B2, then the number, okay, let's write B3, then the number of particles, we know its distribution, and we know that if subsets are disjoint, then the number of particles independent. Okay, so but the question if such object exists or not. And today we will see how we can construct this object. And yes, indeed, we will prove that such object exists. So we can work with this definition. But at first, let me make the following remark or proposition. So when we will produce a construction of a Poisson process, it is important to understand that we construct just the one object then that we need. So we cannot construct 2-point processes with the same with these two properties. And this is easy to understand that if we have 2-point processes, 2 Poisson processes, let be 2 Poisson processes with the same intensity measure, with the same intensity measure. Then we will have the same distribution of these processes. The proof here is very simple. If we recall the previous lecture, when we gave the criteria how we can check that 2-point processes have the same distribution. So we had one of the criteria there that we have that 2-point processes have the same distribution if and only if for any non-intersected subsets B, the vector B1 and so on eta of Bm have the same distribution as here I put prime. So by our assumption in the definition, we know that these random variables are independent, so this and this, and we know their the distribution of each coordinate here. So they coincide because by assumption a Poisson process has the same intensity measure. So by the proposition from the previous lecture, we know that eta is equal to eta prime by distribution. So when we will construct somehow one Poisson process, this will mean that we have uniquely by the distribution a Poisson process. So now we can construct a Poisson process, and we will do this step by step. And first step, let us start from not general intensity measure, but we start from probability measure. And for this, let us give the following definition because we will use it later and now also. So I want to construct some sort of mixing of point processes. So let me fix two distributions. So let V be a probability distribution on n0. So this will correspond to the random number of total points in the space. And Q will be a probability distribution on my space. So this distribution will correspond to the distribution of random points in the space. So all what I need to construct a Poisson process now, I just need to take some distribution of random points, but I need to vary the number of these points. And now suppose that I take x1 and so on, or it will be the unlimited. This will be a sequence of independent or random variable with distribution q, xi distributed by t. And random variable with p kappa has the distribution b, but such that it is independent with all x's here. So I have a family of independent random variables. And now I will form measure define random measure like sum of delta functions at points x, k, where k is from 1 to this random variable. So in this summation, I just add a random number of points at this random number of delta measures at this random points. And this process, eta, is called mixed binomial process. You can recognize here a binomial process if I fix the number of summands. Yes, we considered a binomial process on the previous lecture. So this is a binomial process with mixing distribution. Distribution of V. So this is a number of summands and sampling distribution. So this is how it works. And it turns out that we can construct a Poisson process using this mixed binomial point process. Let's see how we can do this. So the first theorem 1 for today. Let us fix, let Q be a probability distribution. on X and let us fix and some number gamma. So this is a real non-negative number, and kappa has a Poisson distribution with this parameter gamma. So gamma just no. Then mixed binomial process with mixed binomial process with mixing distribution. I can just write Poisson distribution gamma and sampling distribution Q is a Poisson process. Is a Poisson point process. With intensity measure, gamma times Q. So here you see what we can construct, but this is just the Poisson process with finite measure, gamma times probability distribution. So once more, I can represent a Poisson process in this term, in this form, from 1 to kappa, where kappa has the Poisson distribution, and xi from 1 to infinity, iad with distribution q, and I should write that kappa and x's are independent also. So this is the construction. So what we did, so for space x, if I define here some distribution q, so I have here the probability measure, and I take random points with distribution q, and then what I should take, I take the random number of points with such distribution. So if I fix like some subset, I will get the random number of points in this subset. So I will have this. Okay, so let's see how we can prove this. And to do this, I need to check that we have the two properties of the definition. So to do this, let us start to prove property 2. So let's take subsets B1, B2, and so on. Bm, be disjoint subsets Bi intersect Bi is equal to empty, I not equal to J. And let us assume that in union, and in union we will have all our space X. So we just can add to some subset the complement of this union. And in order to understand the distribution of the vectors, so now I want to understand the distribution of random vector v1, vm, I will fix, so what is the distribution? Let me fix numbers, k1 and so on, km be some natural numbers or 0, and let me denote the summation of them by k. And now what we need to do is to see that if I consider this probability, then I can represent it as a product of Poisson distributions. So this is my aim to do. Now, if I know that now I will take a conditional probability. So I will take all of this. This condition, okay, let me write here. I can represent, so I have sum of delta xi of v1 I from 1 to kappa is equal k1 and so on. I equal to xi of bm is equal to km. And now I can take the all possible values of kappa. So if I consider here kappa is equal to k. And here, since we denote that the number of total space is equal to k, then I can just write, okay, I can write here that kappa is equal to k. Yes, since by assumption, the union of all b's is equal to x by this assumption. And if this is true, then in all space, we have exactly k number of points. So I did not add here nothing. But now I can use independence of kappa and x, and I can substitute kappa here. So I just write probability that kappa is equal to k, and here probability of I from 1 to this k exactly. And here delta xi of v1 is equal to k1 and so on. I from 1 to k, delta xi from bm is equal to km. And here the second probability is equal to multinomial distribution. So we, why is it so? So on the first lecture not on the first, but on the second lecture, when we considered example of such a binomial point process, we saw that this is the such process has a binomial distribution. But here, this is a multinomial. So how we can understand this? That at total in space we have k points, but we should choose k1 points in. So we have here a total k points, but we have some subsets. And here we have k1, k2, k3, and so on, k4, for example. And we should choose them. So how do we do this? So this is equal to k factorial over k1 factorial, km factorial. And so this is just the number, how I can choose these numbers of points. And exactly k1 in first set b1, and this is the probability q, because we have the measure of this subset, and so on. The probability of measure of b of the set bm into the power km. Okay, so this is what we have, and we know the distribution of this one. Let me write it just here. So this is gamma to power k over k factorial e to the power minus gamma. So now I can split this k into summands. So now I can produce here the probability, what is equal from 1 to m. So I just write, so I split gamma to the power k1 k2 plus k2 plus and so on km, and I took it together with this one. So this to the power k yod divided by k yod factorial, and also I split this gamma into such parts. So since I know that q is probability measure, so in sum it gives me 1. So I have the product, and you see here that each term is the Poisson distribution with this parameter. So this is a Poisson distribution with this parameter. So this shows us that indeed we have that these random variables, eta of b1, eta of b2, and so on, beta of bm are independent. And has the have Poisson distribution. So in order to see that each, for example, eta v1 has Poisson distribution with parameter gamma by q of b1, you just need to sum over all other values, and here you will see that in summation you just get 1. So you just get one term in this product. Okay, so this proves the statement that shows us that we can produce a Poisson process with measure of the form here, just number times probability distribution. But in the definition, we gave the definition for as finite measure. So now we need to understand how we can produce as finite, how we can produce a Poisson process with as finite intensity measure. And for this, we need to prove some additional statements. And they are the following. So if we have, let us think a little. So if I have some Poisson process with finite measure, how I can get infinite, how I can get a point process with infinite intensity measure. So the idea, we can use the previous proposition and then add accountably many Poisson processes in order to get one with as finite intensity measure. So with this idea, let us prove this technical result, and also we will use it later, that if I have a sequence of independent point processes, if I sum them, I again will have a Poisson process. So let's write it. Let eta I from 1 to infinity be a sequence of independent, here this is important, independent Poisson processes on X with intensity measures, intensity lambda I. So each a process has its own intensity measure. Then, if I consider the sum of random measures, this eta, then this eta will be a Poisson process with intensity measure so just we need to add intensity measures. So you see why we need this as finite measures, because when I have as finite measure and then I sum them, then I again will have as finite measures. So these measures does not will have the same class as finite. So how we can prove that? So at first we can see that eta is a point process indeed, point process. How we can see this? We just see that this measure eta belongs to class of measures that we defined. So we defined class of the measures n as a countable sum of finite measures. Yes, so yes, indeed, this is a countable sum, and it is measurable, mapping from omega to n, since we have here, so you know that the sum of random elements is a random element again, and the limit of random elements is a random element again. So what we need to prove is just that this process has properties of a Poisson distribution, and to see this, let us check two properties. So the first property, let us consider a finite sum, because it's easier to work with finite sum. And let me define psi n of b will be just finite sum I from 1 to n. And this has the Poisson distribution. I believe that you check it maybe on in general course of probability theory, that the sum of we checked it on our first lecture when we consider the property of Poisson distributions. We saw that the sum of independent Poisson distribution again is a Poisson distribution. So if I have a sum of independent Poisson distribution, this will be again a Poisson distribution with parameter what I have just summation here from 1 to n. So this is we know. So how we can get to the limit? So let us just consider the probability that eta of b is less than k. Then since I know that psi n of b increasing to eta of b, yes, we know that we add non-negative variables, then we can use monotonicity of probability measure. So this will be the limit when n tends to infinity, and here probably that psi n of b is less than k. So now I can write this probability. This will be sum from 0 to k. Yes, I just add all values from 0 to this k. And here I should write the probability that this value is equal to k. So I just write this probability e to the power minus, so this is a parameter I from 1 to n lambda I of b, sum I from 1 to n lambda I of b to the power k to the power y over y factorial. And I write this formula not just to recall it, but to see that if now I can change the summation and limit, and here this function is continuous with respect to this parameter. So it is continuous. So when I have continuous, the limit of this continuous function, this one, then I can get to the limit. So I will write here minus, and now here I put infinities here. And by the definition, I will use here lambda from b. lambda from b to the power j factorial. So I can see that this probability is equal to just sum of, I'm sorry, here k. So this is the cumulative distribution function of a Poisson process. So this is just by the definition, eta of b has Poisson process with parameter lambda of b. Okay, now the independency, how we can see that for non-disjoint, this is the second property. For all fixed m, let B1 be M disjoint subsets and then these random variables Bi are independent. Why is it so? So we know the independency for all, we know by assumption. We know that Bi from Bj, where, so this says where I have j from 1 to m and I from all indexes. So this is the family of independent random variables. It's a family of independent random variables. Why is it so? Because we assume that point processes eta I are independent and they itself they're independent on for disjoint subsets B. And now if we will form from this family of independent random variable, if I form such sums, j from 1 to, then I will have independent random variables again. Are independent. So this is just because we group independent random variables such that for each here for each B1 and Bm, B2 and so on, they are independent. And if we group them in such a way, then they are independent again. So from this follows that we prove the statement because we prove that such the sum of Poisson processes of independent Poisson processes will be again a Poisson process with such intensity measure. So this gives us the idea how we can produce a general Poisson process if we know how we can produce a Poisson process for finite measures here, so we can produce. And this is the main statement. Theorem 2. Let's just state it because now we understand how we can prove it. So this is the existence theorem. Let lambda be an S-finite measure on X, then there exists a Poisson process on X with intensity measure. Now, so let me write the steps that I talked already. So for the first step, if lambda of X is trivial, so this is very easy because we understand that this is just a point process that nu of X is equal to 0 with probability 1. So this is just 0 measure. It's not interesting. So now the case when lambda of all space is finite, then we can, on a probability space, we can define mixed binomial process with what parameters. So we just take kappa is a Poisson distribution of this parameter at lambda of X. Okay, and X I are independent ID with distribution just measure lambda divided by lambda of X. So I just write here the normalization in order to apply the previous result, because we prove it for probability distribution. So here we have exactly the previous result, and from the first theorem it states that okay, I should write here that kappa independent from xi. So this process xi from 1 to kappa, Poisson process with what parameter? So with intensity measure, So what did we write? We write Q times parameter of this Poisson distribution. So this is lambda of all space by lambda dot lambda all space. So this is just lambda, so that what we claimed in our proposition. So now third case, if lambda of X is equal to infinity, but we suppose that lambda is as finite. So what does it mean? That lambda can be represented as sum of finite measures. Maybe so, where lambda I are finite measures. So now we just can say that there exists independent, we can construct independent Poisson processes, So this is by the previous step. We define independent Poisson processes with intensity measures lambda I. And the last step, using that the sum of independent Poisson processes, again a Poisson process, we define this Poisson process as sum of independent paths And by previous statement, this is a Poisson process with intensity measure lambda, which is equal to sum of lambda i's. And this is the end of the proof. So today we saw how we can construct a Poisson process. And for this, we use so-called mixed binomial distribution. Yes, so, and we saw that a Poisson process can be represented in such form. So here we just consider the sum of random number of delta measures at some random points. So this is the main idea how we can construct a point process. You just take here a Poisson number of random points, and you can get a Poisson point process with any intensity measure you want. Okay, so this is all for today's lectures, and thank you. See you next time.